All right, so in this video, I'm going to go through setting up the initial conditions when solving a second order circuit here. So what I have here in the top right is going to be a repeat from the previous video on just general methodology. So I just want to, I would just highly recommend that you have that available so that you remember what steps we need to take as we're tackling this circuit here. So the first thing that we want to do is, again, we want to take this into 4 different parts, and I have it somewhat laid out here. And again, all we're doing here is we're just setting up the initial conditions. We're not going any further at this moment. So to begin, the very first step is looking at what is happening to the circuit when time is less than 0. So we want to figure out what the current is, what's going on with the current here. So before you do that, one thing you could do is you can go ahead and redraw the circuit just so you have a visual understanding of what's going on. So when time is less than 0, the switch is already open, which means, let's see. So, I'm sorry, it should be closed and then it opens up at time equals 0. So if it begins closed here, then what's happening is that your inductor should act like a short and your capacitor should be open. So what you're left with is essentially just a 2 resistor series with the source here. So it's 20, 5 and 3 like so. So this is fairly easy to now tackle here. So the current of the circuit at time less than 0, we can essentially just use Ohm's law here and V equals IR, but transforming it. So V over current is equal to V over R. So that's 20 volts divided by the sum of the 2 resistors, which is going to be 8 ohms. And that's going to give you 2.5 amps. Next, we want to look for the voltage that's across the capacitor, which also happens to be the voltage at this point here. So we're looking at the point in between the 2 resistors. Hopefully what you can see here very quickly by now is that this is actually a voltage divider. So to find the voltage across the capacitor, we take our source voltage, multiply by the resistor that we want over the sum, and we go ahead and solve for that. You end up with 7.5 volts like so. All right, so once we have that, we've completed the first step because we found the current through the circuit and also the voltage across the capacitor. We now move on to the second step here. So the second step is going to ask, well, what's happening with the current right when the switch activity happens? So this is I at t equals 0, but like really soon, right when the switch activity actually happens. And I kind of give a hint here because when the current, the current of the circuit when right when the switch activity occurs, because you have an inductor and capacitor, because you have an inductor in there, you actually don't want the change of current to happen immediately. Eventually it will, but we're looking at like right when the switch actually happens. So the hint here is that at that point, that sudden point, the current is actually the same as the current beforehand. So one thing that we can do is we can actually use this shortcut to, or this concept, this knowledge to actually make the connection that, well, because I know that the current is not going to change immediately, I know that my current is going to be the same as what it was at time less than 0. So therefore, the current is still at 2.5 amps. Same goes with the voltage as well. So the voltage of the capacitor, it's already fully charged up with all the voltage, and right when the switch activity happens, whether it's open or closed, in this case it's an open. Well, at that point of the switch opening, what's essentially the starting position, or what's the starting amount of voltage of the capacitor here? And again, we can make the connection that that's the same as what it was at when we were examining time is less than 0 here. So we can make the connection that it's actually equal to 7.5 here. Third step, you want to look at the transient period. So this is looking at dV, dt, and we can go ahead and use the formula, the current of the capacitor divided by the capacitance as to solve for this circuit. Now, the transient period, now that the switch activity has occurred, your new circuit should look like this. So you should have a source, you have a resistor, you have an inductor, and now that middle switch is open now, everything's going to go through the capacitor. So now we have 20 volts here, 5 ohms, 0.5 henries, and 0.2 farads, like so. So knowing our equations, knowing that dV dt of the capacitor is equal to the current across the capacitor divided by the capacitance, we can go ahead and use our knowledge, or what we have before. We know that the current that's going through the capacitor, in this case, since it's a series, we know that it's actually this 2.5 amps right here. So 2.5 amps divided by 0.2 farads. That's going to give us 12.5 volts per second, like so. So again, this should be a rate of, this is the rate of change of the voltage. So for the voltage across the capacitor now, at time greater than 0, we actually need to use KVL, Kirchhoff's voltage law, to figure this out. So go ahead and move this up just a little bit more space here. So if we were to use Kirchhoff's voltage law, we start at the source here, so that's 20 volts minus your current times your resistance, or it's another voltage here. So this is going to be 2.5 amps times 5 ohms minus the voltage across the inductor, which is what we are solving for. We don't know what that is. Minus what's the voltage across the capacitor? We know that it's 7.5, like so. So that's minus 7.5 volts. All that's equal to 0. So if you actually go ahead and solve for this, you'll actually find or figure out that the voltage across the inductor is going to be 0. And it does make sense. So did we have to do this? No, not really. But what I really wanted to show was the fact that, again, we're looking at the period where we're looking at the immediate voltage change that's actually happening with the inductor. And it's actually going to be 0 in this case, which is true because when it comes to the inductor doesn't want that current to change. So the transient period, at least, is going to be 0, like so. And likewise, when it comes to the current, the change of current in the inductor, hopefully didn't really spoil it in the last variable that we solved for, but it's essentially 0 volts divided by 0.5 henries, which will give you 0 amps per seconds. So same story goes with the current as well, the current of the inductor. Lastly, we have the steady state here. The steady state, so when time goes to infinity, basically the circuit will now look like this after a long period of time. So you have your 20 volt source, so 20 volts, and then your 5 ohm resistor, and your inductor will act like a straight wire, and then your capacitor will be fully saturated, and it'll just be open like so. So now, knowing that to be your steady state circuit, what is the current of the inductor when time goes to 0, or time goes to infinity, sorry? It's going to be 0, spoiler alert there. And then what's the voltage across the capacitor here? Well, it's going to be 20 volts. All right, so this is just setting up the initial conditions. We're not solving for this differential equation yet, or the second order circuit yet. But all I'm showing here is just setting up the initial conditions. I'm doing it, we're kind of presenting it pretty slowly, just so you kind of know, you create this system or the procedure list of how to solve for these circuits, and eventually we'll put it all together.